If we remember that the response of a harmonically forced dynamic system is given by ut equal to the initial displacement times by cosine omega nt plus the initial velocity divided by the natural frequency, subtracting from capital omega p naught, natural frequency times by the stiffness, times by 1 minus capital omega squared divided by the natural frequency squared, all times by sine omega n t plus p naught over k times by 1 over 1 minus forcing frequency divided by the natural frequency, all squared, times by sine capital omega t, with a typical response that looks like this. Again, normalizing the time axis by the natural period. We have our steady state response shown by the dashed line and our transient response oscillating around this line by the solid line. The steady state response we denote by U subscript double S, and that's equal to P naught over K times by 1 over 1 minus the forcing frequency squared divided by natural frequency squared. And this is times by sine capital omega t. This can be viewed as the structural oscillation at the forcing frequency capital omega due to the applied force. The transient component shows the oscillations of the structure at the natural frequency of the system. This exists even when we have zero initial velocity and initial displacement. We can show this, for example, when the initial velocity and the initial displacement are equal to 0, then our transient component is equal to P naught over K times by 1 over 1 minus the forcing frequency squared divided by the natural frequency squared times by sine capital omega t minus capital omega over the natural frequency times by sine the natural frequency. So this is the transient component with the initial conditions set equal to 0. And we can see it still exists because we made the argument this is due to the inherent dynamic properties of the system. We can define the ratio of the forcing frequency to the natural frequency as beta, and the static displacement as U static equal to P naught over K. Equation 3 then becomes ut equal to u static times by 1 over 1 minus beta squared times by sine capital omega t minus beta sine omega nt. The steady state dynamic response is then u subscript double s t equal to u static times by 1 over 1 minus beta squared times by sine capital omega t. If we now return to our equation of motion, which we will repeat here as the inertial force plus the stiffness, and we look at the forcing function as well, then if we ignore acceleration, then we can say that Ku is equal to P naught sine omega t and Ut is equal to P naught over K times by sine omega t, which is equal to U static times by sine omega t. We're ignoring acceleration in this case because we're only considering the static component of the equation of motion. We can then see that the maximum value of this deformation is just the amplitude U static. So the remarks from this are, firstly, 1 over 1 minus beta squared. This is the magnification effect of the applied harmonic loading. Sine capital omega t. That is the response component at the frequency of the applied loading. And beta times sine natural frequency t. That is the response component at the natural frequency. This last component here, in our later studies, we will see that this will vanish for systems that contain damping. This is why it is called the transient response. Finally, the response ratio, R of t, is the ratio of the dynamic to static response. So we say that we have the dynamic response ut divided by u static, which is equal again to ut divided by p naught over k.